What is bracing and its common types? Bracing is installed in structures in order to provide stability and resistance against lateral loads. While beams and columns support vertical or gravity loads, bracing is installed to resist horizontal loads, such as wind, that act on a structure. The most common types of bracing are K-bracing, cross-bracing, and single diagonal strut braces. K-bracing is less common than cross-bracing and single struts, but we'll examine it first because it's more straightforward. Understanding how K-bracing works will provide a foundation for comprehending how bracing functions in general. If you look at this photo here, you'll see an example of K-bracing. If you tilt your head, you'll notice why it's called K-bracing. It forms a K shape. K-bracing is often installed in structures to provide resistance against large lateral loads, such as those caused by earthquakes. If an earthquake occurs, it will cause the entire building to shift back and forth, making the building sway in various directions. To understand this better, let's examine one direction at a time. Looking at this image, you will see that the entire building will deflect to the right in one movement. This will exert a lateral load on this beam here. As this occurs, this member will be pulled, and this member will be pushed against. So, as you can see, there are two parts to a K-brace. One member is used in tension, and the other is used in compression. When the building moves in the other direction, the opposite will happen. This member will be in compression, and this one will be in tension. Ultimately, a K-brace works by transferring the lateral load caused by the earthquake downwards into the columns and eventually to the building's foundations. Now, let's take a look at cross-bracing. Cross-bracing is more common than K-bracing and is something most people are familiar with. While cross-bracing is different from K-bracing, it works in a similar way. When a load, such as wind, acts against the side of a building, it will cause deflections and sway. If wind blows against this building, for example, from the left, the building will deflect to the right. As this happens, this member will be pulled in tension, while this one will be pushed and put into compression. One thing to note about cross-bracing is that the members used are usually lightweight, as only the member in tension actually provides resistance. This is because thin members have poor compressive capacity. In other words, one member at a time resists the lateral loads. So, when lateral forces come from one direction, one member will act in tension. And when lateral forces come from the opposite direction, the other member will act in tension. An alternative to cross-bracing and the other common type of bracing is single diagonal brace or strut. Single diagonal bracing has its own applications. For example, if an architect wanted to place a door here, a diagonal cross-bracing member would be in the way. With single diagonal bracing, a single member is installed that is strong enough to resist lateral loads in both compression and tension. If you look at this example, you will see that when lateral forces come from this direction, it will be put in tension. And when they come from this direction, it will be put in compression. Obviously, in this case, the single strut needs to have both good tension and compressive capacity. As a result, it is common to find larger hollow steel sections or universal columns being used as single diagonal members. These are much heavier compared to cross-bracing members, where much thinner steel can be used. This is an important note when comparing cross-bracing and single struts. Cross-bracing is usually cheaper to install than a single diagonal strut, because the thinner members are lighter and cheaper to fabricate and install on site. In summary, Regardless of the bracing type, the brace members will undergo either tension or compression. Tension members are smaller in size, and even a steel rod can be used. However, much larger members are required if they need to be designed to carry compression loads. This is mainly due to a failure known as buckling, where the members suddenly move out of their plane. This happens only to compression members, and often governs the member size, especially when the member length is increased. Now, you may ask, what kind of steel sections can be used for a bracing element? Well, there is a wide range of steel members that can be used to create bracing elements. In fact, it is even possible to use very lightweight steel members, such as steel rods or flat plates, when the braces are only working in tension. Light equal angles, EA, or unequal angles, UA, are also very common as tensile members for cross-bracing. Equal angles refer to an L-shaped section with two equal legs. Their leg size ranges from 25 millimeters to 200 millimeters. For each size, there are multiple types based on the plate thickness. As you can see, it is identified by three numbers, where the first two numbers refer to the leg size, and the third number indicates the section thickness. On the other hand, an unequal angle, as the name implies, has unequal legs. Similar to the equal angle section, it is identified by three numbers, where the first two numbers are the leg lengths, and the third number is the plate thickness. While heavier parallel flange channels, or PFC, hollow sections like SHS, RHS, CHS, and even UB and UC sections are often used in members that will experience significant compression forces, as well as tension. Our previous examples of bracing have focused on its application vertically within a structure. However, these forms of bracing can also be used horizontally. To explain this, let's look at the example of a wide portal frame structure that is subject to a wind loading from left. Previously, our facade spanned across the entire front of the building. When wind loading impacted this facade and caused it to deflect, the force was transferred into the wall bracing via the tie beams located along the edges here. However, if we increase the width of the building so that it's not possible for the facade to span across, the situation will be different. In this case, it will be necessary to install another line of columns down the center of the building with tie beams between them. Now, to transfer lateral loads from the central columns and tie beams to the vertical bracing in the wall, cross bracing needs to be installed horizontally in the roof. Alternatively, vertical bracing can be installed between the central line of columns. However, this will take up space in the building. In this example, a combination of both methods has been used. Now, let's understand how horizontal bracing works with vertical bracing to withstand lateral loads. If wind blows against the facade of this building from left to right, a lateral force will be transferred down the building through this central row of tie beams. When the tie beam deflects in this direction, the column also tends to move to the right. However, the roof bracing members will resist this movement by undergoing tension. As these members are put under tension, the load will be transferred to the vertical wall bracing and subsequently to the building foundation. On the other hand, if the wind blows against the facade of this building from right to left, a lateral force will be transferred down the building through this central row of tie beams. As a result, the column wants to deflect to the left. This time, the other set of horizontal cross-bracing members will resist this movement by undergoing tension and transferring the load into the wall bracing and foundations. As you can see, in this example, one set of bracing works in tension at any given time, depending on the direction of the lateral load, to resist the force. Note that bracing is not the only way to make a steel structure resistant against lateral loads. For example, where rigid precast panels in between columns are used to do the same job. You can see the example here. Another alternative solution to resist lateral loads in a steel frame is to detail rigid connections between beams and columns. This approach increases the frame's stiffness against lateral movement and provides resistance to lateral loads. These frames, known as portal frames, offer the main advantage of providing an open space. It is important to note that for any given structure, lateral load resisting systems must be detailed in two perpendicular directions. For example, in this case, a combination of roof bracings and wall bracings are used to provide lateral stability in one direction, while a portal frame is detailed in the other direction. As you can see, there are many solutions to the same problem. This is why it is important for engineers, architects, and builders to work together to develop a solution that ticks all the boxes, not just structural integrity. See you in the next video.